This lesson on descent performance will focus mainly on the forces in the descent and what factors govern the descent. In a normal flight, the descent will occur at a point we define as the top of descent, which may be up to 200 miles before the destination aerodrome. A descent will also be required following engine failure or depressurization. In this latter situation, the descent is forced early, and it is important for the pilot to be aware of what determines the characteristics of the descent so that obstacle clearance can be maintained. There are two ways of measuring the descent performance of an aircraft, either by angle of descent, sometimes called descent range, or rate of descent, sometimes called descent endurance. Firstly, let us consider angle of descent. Shown here is an aircraft in level flight with the forward forces balancing the rearward forces. Thrust in this case is balancing drag. In order to initiate a steady descent, thrust is normally reduced. Notice that the rearward force of drag exceeds the forward force of thrust and the aircraft slows down. The value of drag that exceeds the thrust force is called excess drag. In order to balance the forces and maintain speed, the nose is lowered until the weight apparent thrust provides enough forward force to balance the excess of drag. Now the aircraft will maintain this steady descent angle at a constant speed. The forward and rearward forces are in balance once again. Notice that the drag force is being balanced by both the engine thrust and the weight apparent thrust. The weight apparent thrust can be calculated by multiplying weight by the sine of the angle gamma. If thrust were reduced even more, then there would be a greater amount of excess drag. More weight apparent thrust is therefore needed to balance the greater amount of excess drag. To gain more weight apparent thrust, the aeroplane nose must be lowered even more. The result is an increase in the descent angle. For the purpose of the examinations, lowering the nose is also described as decreasing the pitch angle. From this demonstration, it is clear that it is the excess drag which determines the angle of descent. Notice that the angle gamma is the same angle as the angle of descent. Rearranging the formula on screen so that angle gamma can be calculated gives us the formula for the angle or gradient of descent. Drag minus thrust will give excess drag. In summary then, the angle or gradient of descent is controlled by the excess drag. In order to visualize this excess drag, it is necessary to return to the thrust and drag graphs that were used in the climbing lesson. Shown on screen are the thrust and drag curves for a jet and propeller aeroplane. We have learnt that in order to descend, there has to be an excess of drag. On the graphs, excess drag can be found by taking the area beneath the drag curve and subtracting from it the area beneath the thrust curve. The highlighted areas represent excess drag. Notice that if thrust is reduced at any given speed, then excess drag increases. Therefore, the descent angle increases, just as was shown on the forces diagram. If it were a performance priority to maximize the angle of descent, then from the theory we have seen so far, we would have to maximize excess drag. If thrust is reduced to 0, notice that the excess drag area is a maximum, but to obtain the maximum excess drag, the aeroplane needs to be accelerated to a very high speed, as shown. This can be achieved by closing the throttles and continuously lowering the nose of the aeroplane so as to cause the increasing amount of weight apparent thrust to accelerate the aeroplane. As speed rises even more, both the excess drag and the angle of descent will increase. The angle of descent, then, is a function of excess drag. The greater the excess drag, the steeper the angle of descent. This angle can be increased even more if it were possible to increase the excess drag. This can be achieved by deploying drag devices such as the speed brakes and the undercarriage, but attention must be paid to their maximum deployment speeds. The practical side of increasing drag to increase your descent angle occurs mainly in training and occasionally in commercial operations after air traffic reroutes. Take note that any increase in excess drag, either by deploying flaps or undercarriage, or by reducing thrust, will steepen the angle of descent. You have just learnt that to maximise the descent angle, excess drag must be maximised. In this part of the lesson, you will learn how to minimise the descent angle. Following an engine failure, the aim is to ensure that the aeroplane will cover the greatest horizontal distance so that the pilot has a large area in which to select a suitable landing field. This can only be achieved by using the flattest possible angle of descent, sometimes referred to as the minimum glide angle. To understand how this can be achieved, let us return to the aircraft in straight and level flight. If the engines were to fail, then to balance the excess of drag, which in this case will be the entire drag force, the aeroplane's nose must be lowered by a sufficient amount to create enough weight apparent thrust to balance the excess drag. The aeroplane will now maintain a steady speed in the glide. If drag were to be decreased, then notice that weight apparent thrust can be decreased by raising the nose by an appropriate margin in order to decrease the angle of glide. From this you can see that if drag were reduced to a minimum, the angle of glide will also be reduced to a minimum. This can also be seen in the graphs. Notice that VMD is the speed found at the bottom of the drag curve. At VMD, drag is at a minimum. Therefore, to descend at the minimum possible angle, the aeroplane must be flown at VMD. Shown here is an interactive demonstration allowing you to change the value of drag and observe the effect on the angle of descent and subsequent descent range. Move the drag slider on the right of the screen to observe the effects. Once you have finished, click on the flashing arrow to continue. One of the other ways to examine glide performance is to consider the aeroplane's lift-over-drag ratio, commonly referred to as the lift-drag ratio. However, before we do this, there is a little more detail on the forces diagram to discuss first. Notice that in the glide descent, the resultant of drag and lift balances the force of weight. From your Principles of Flight lessons, the term for the resultant of lift and drag is total reaction. If the drag force line is moved upwards, you can see that we now have a triangle of forces, with the angle gamma being the angle between the lift and total reaction. From the bigger picture, which shows the aeroplane's glide angle with respect to the ground assuming no wind, it is easy to prove geometrically that the angle gamma is the same as the angle between the aeroplane's glide path and the ground. Consequently, from the triangle of forces, it is clear that if there were any change in the lift and or drag values, both the angle gamma and the glide angle would change. A typical modern jet has a maximum lift-drag ratio of about 19. Where this ratio reaches its maximum value, the angle gamma will be at minimum. The lift-drag ratio reaches its maximum value at 4 degrees angle of attack and at the speed VMD. Therefore, VMD is the speed for the minimum angle of descent or the minimum glide angle. VMD is also known as a speed for LD max. The angle of attack at VMD is fixed at 4 degrees. If the angle of attack is greater or less than 4 degrees, the speed will change, the lift-drag ratio will decrease in value, and consequently the angle of glide will increase. If, following an engine failure, you fly at VMD, your aeroplane will be flying at the flattest possible glide angle. Never try to stretch the glide by raising the nose of the aeroplane. If you do so, the speed will decrease and the glide angle will steepen. At any speed other than VMD, your glide angle will be steeper than the optimal glide angle. Shown on screen is the angle of glide at VMD. The temptation is to raise the nose a little. This gives an impression from the cockpit that the glide is being extended. Looking at the diagram, if the nose were raised, the weight apparent thrust would decrease and the aeroplane would slow down. As a result, the aeroplane would not be flying at VMD and therefore not have the best lift-drag ratio. The result would be a steeper descent angle despite the fact that the aeroplane had a slightly higher nose attitude. Be disciplined in following the procedures for flying at the optimum glide angle as laid down by the manufacturers or the operator in the aeroplane flight manual.